Imagine that you have a deck of cards. Each of the 52 cards has some information on it, like the color, red or black, the suit, clubs, diamonds, hearts or spades, and the rank, ace, 2, 3, and so on, jack, queen, and king. You can arrange the 52 cards in many possible ways, but if you want to organize them, it's probably you will end with something like this arrangement. Suits on the rows, ranks on the columns. It's easy to organize because you know there are 52 cards of 4 different suits with 13 different ranks. Something similar happened with the elements, although scientists at the time wasn't sure what an element was, nor how many of they were, and the suits and ranks weren't either that clear. It became a puzzle, the puzzle. During the Antiquity until the Middle Ages, there were only 12 known elements. But wait, what's an element? It's a substance that cannot be separated into simpler substances, either by physical or chemical means, without losing its characteristics. An element consists of the same type of atoms. The same type of atoms have the same number of protons. 52 elements were known by 1849. By then, chemists noticed that some of them behave similar. For example, when you add water to the metals lithium, sodium, or potassium, they react violently with an explosion and emit a gas, hydrogen, which is highly flammable. On the contrary, the gases helium, neon, argon, krypton, xenon, and radon hardly react with anything and were particularly tough to discover. This makes scientists wonder, is there a way to organize this information? Several scientists attempt to solve the puzzle, but we owe the organization we know to Dmitry Mendeleev. He was smart enough to think we haven't discovered all the known elements yet, and therefore he put a placeholder to fill in the gaps in the puzzle. Even more, he was able to predict how these missing elements will look like, how much will weigh, and some other characteristics. Was he a fortune teller? Nope. He just recognized that these characteristics were appearing from time to time. They were periodic. And yeah, that is why it's named periodic table. We can also think about the periodic table as a map. An element's attributes depend on the coordinates where it's located. In this case, the coordinates are called groups or families for the columns and periods for the rows. The periodic table has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 groups and 7 periods. Now, let's zoom in. We identify elements with a name, but names are often too long for easy reading in a table, so we have a symbol for each element and also a number. Remember that an element consists of atoms with the same number of protons? As soon as an atom gains or loses a proton, it becomes other element. The number of protons in an element help us to identify them, and it's called the atomic number. Also, elements are neutral. This means the number of positive charges and negative charges has to be the same. If we know the number of protons with positive charge, we instantly know the number of electrons with negative charge. Another important piece of information is the mass of an element. The mass number is the sum of the number of protons and neutrons, and both are located in the nucleus of an atom. Generally speaking, heavier atoms are found at the bottom and the right of the table. The mass increases when moving up to down from period to period and right to left from group to group. Like any other map, there are continents and countries. Here, on the left and middle of the table, we find the metals continent, which include the lanthanides and actinides. Although they are usually depicted at the bottom of the table in 2 separate rows, they are here, between barium and hafnium and between radium and rutherfordium. Then we have a staircase boundary of metalloids, and on the upper right side we can find the non-metals continent and the hydrogen. Metals are good heat and electrical conductors, malleable and ductile, and with the exception of mercury, all are solids at room temperature. They love to combine with non-metals and are willing to give in them their electrons. Non-metals are poor conductors of heat and electricity. If they are solid, they are brittle, but you can also find liquids and gases, and usually gain electrons when combined with other elements. Following up map analogy, a region can be found by several names. Then, for example, group 1 is also called 1A, or alkali family. Group 2 is also known as family 2A, or alkaline earth metals. Then we have the B families here. Then we jump to group 13 to be named 3A, 4A, 5A, 6A. Then 7A is also known as halogens, and 8A is also known as noble gases. Here a quick hint. The name of the group is related with the number of electrons they have to combine with other elements. Then, for example, lithium and sodium in group 1A have 1 electron to mix. Carbon and silicium in group 4A have 4 electrons to share. The elements in group 7A has 7 electrons to combine. The periodic table is the map of all the elements known to man, the same elements that exist in the universe. Some occur naturally and are very stable, and some others exist only fractions of seconds after synthesis. Because of all the information that contains, is a powerful tool used by chemists and scientists every day, and was and will be a map of the history of everything and a window to the future.